Okay, welcome to the last session of today's talk. The speaker for the last talk of today is Professor Arindam Ghosh from Department of Physics, IISc Bangalore, and he's going to talk about hydrodynamic flow in graphene.
Okay, I wish to thank Rajesh and Abhishek for this opportunity. It's been a wonderful conference and wonderful talks, very steep learning curve. And I kind of will overlap a little bit with what Suvir has said, what um, Mandar had said in the morning today. I think, there are a few talks that uh, come later also, which have some overlap with the kind of topic that I'm going to talk on. Overall, my work will be looking at graphene and some of the recent experiments that we have done, but I was told that this would be a more pedagogical talk, so there are ways in which I'm going to introduce things to people who are not experts in it. Uh, People who have done the work, uh, they are mostly here and had posters as well. And my theoretical collaborator, Shubhrata, I don't know, think Shubhrata is here today. And of course, collaborators from Japan who provide wonderful quality of boron nitride. So the theme would be how we can make condensed matter systems coupled to holography in some ways, in which we look at possibilities of what are the materials, how we can connect better, make representations and look at the predictions from ADS safety mapping. There are people here who are far bigger experts in this topic than I, but my goal will be to essentially look at certain aspects of graphene that can pull out that create a beautiful platform which we can build on because of the quality of the graphene that we have started making after 20 years of its evolution can lead to wonderful theoretical verifications or even lead to something new. So cold atom community, of course, has been the forerunner in this whole concept of creating analogs of black holes in many ways through this ADS-50 conformal mapping. But condensed matter systems are catching up. For example, strongly correlated systems, for example, the strange metals, high TC superconductors, they have already been discussed in this context. Semiconductor nanowires, topological insulators are also systems that are quite popular in looking at possible application of various holographic models into condensed matter systems, tabletop systems today. Graphene is of particular interest because of the simplicity of the material. It has got a very well-defined lattice. We can make extremely high-quality graphene in the laboratory these days. It sort of kind of avoids the complexity of multiple elements inside the same system. So that's one of the reasons why many groups now in the graphene community is looking at it. Graphene has already been one of the very popular platforms to realize high energy or astrophysical phenomena. For example, Klein tunneling, where you have a tunnel barrier through which electron can tunnel as a whole and go in the other direction, simply because of the zero band gap nature of graphene. Then the Schwinger effect, in which you apply a large electric field, and it can be shown that the electric field essentially leads to pair production of electron and hole. That has also been demonstrated with graphene as a platform. And of course, if you look at the duality of the through the SYK model, there are theoretical, as well as some recent experiment I have seen from Philip Kim's group, essentially looking at disordered graphene quantum dots. Essentially, the irregularity at the edges lead to randomness in the fermion coupling without destroying the chirality of the charge itself. So there are various theoretical as well as experimental developments in using graphene for various, to demonstrate the gauge gravity duality for a while now. So why graphene is such an interesting system? Again, go back a little bit. So the idea here is that because of the fine structure constant in graphene, which is instead of the speed of light, we have got the velocity of electrons, which is nearly 300 times smaller than that of light. The electron interaction, which is the effective fine structure constant, is nearly an order of 1, which means it's an extremely strongly interacting system. And that leads to the possibility that at the Dirac point of graphene, there is, it sort of evolves into a Lorentz invariant quantum critical point, where you start seeing this physics that we saw in the morning today, that possibilities of electron hole scattering at the Planckian rate and various universal transport properties and so on and so forth. So let's understand a little bit of, with schematic, maybe a little bit oversimplified, what happens. So if you have graphene at the Dirac point, where there is no Fermi energy per se, there's no Fermi surface, it's just a point there, and your whole thing is at a temperature T, then there are excitation of holes into the graphene, and which leads to some form of effective momentum. And the whole thing is a linear band structure. So we can, this region is essentially an electron hole plasma, which if you apply electric field, they start banging against each other. And if this whole thing is at the quantum critical point, then these collisions occur at what we call the Planckian rate, given by kBt over h cross, and this is what you call a Dirac fluid. This is a term that we have developed. Now, if I have such a system, then what is the electrical conductivity? What can you estimate that? And it turns out you can. So if you take a look at the conductivity when this Fermi surface is at this point, then you have 2e squared by h multiplied by the momentum multiplied by the mean free path, where this number is essentially given by this one multiplied by the L is velocity multiplied by the time, and the time is the Planckian scattering time. These all cancel out in certain ways. And in the effect, you expect the conductivity of graphene at the Dirac point is something which is material independent as such, something in the order of e squared by h, which is very good, but you can also have a Fermi surface by inducing carriers in graphene, and if that happens, then through relativistic hydrodynamics, being this one being at a quantum critical point, you can look at this as the overall electrical conductivity as a function of density, where it's a universal constant multiplied by something which is n square, and this is the enthalpy density. If you use this system and do Boltzmann formalism, you can get from electrical conductivity, you can get the thermal conductivity as well, where the thermal conductivity K kappa is inversely proportional to the electrical conductivity, which is something which is unusual. Now, so if I summarize what I just said, in a standard diffusive electrical conductor, you have the Wiedemann-Franz law, where electrical conductivity and thermal conductivity are directly proportional to each other. In the case of a Dirac fluid, exactly the opposite that takes place. You have the electrical conductivity and thermal conductivity are inversely proportional to each other, okay? And in addition to that, the effective Lorentz number, which is universal in case of a diffusive kinetics, becomes a density-dependent quantity that breaks the Wiedemann-Franz law completely. In addition to that, a Lorentz number also gives you the entropy. This is essentially a ratio of two transport coefficients. It gives you an experimental handle to what kind of thermodynamic properties as well. So you can measure them by measuring the Lorentz number experimentally. Okay, so what is the problem in this? Experimentally, it turns out the problem is most of the temperature above, say about 200 to 300 Kelvin, are difficult to access because of the phonons. We are talking about a solid state analog to look at certain high energy phenomena or certain strong correlations phenomena in which we don't want our momentum to relax, but if you have too many phonons in the system, the momentum scattering, relaxation takes place. So this energy scale or the temperature scale is pretty much difficult to access. Another problem is on the other side, that when you go below, at lower temperature, where you have closer and closer to the Dirac point, the system becomes inhomogeneous in nature. There are calculations, this is from Suffolk Adams group, and it looks like that there is temperature range of about 100 to 200 to 300 Kelvin, where probably you can look for possibility of graphene becoming a representative of what you call a Dirac fluid. So the problem is that if I take graphene on various substrates, and Mandar talked about HBN today, you can put graphene in good quality substrates and make high mobility graphene. And if your mobility is sufficiently large, what happens is the density at which your inhomogeneity sets in becomes smaller. You can see the higher mobility, which on boron nitride, the mobility is much higher, and this is where the minimum density that you can achieve in a graphene sample becomes smaller as well. And this sigma minimum that you can measure in an experiment with a real graphene device becomes different for different values of mobility. And this is an incompressible region. And because of n min is so large, about 10 to the 11 or so, it makes it extremely difficult for experiments to access the Dirac point where the system really becomes quantum critical. Okay, so this is the problem we'd like to solve. If you take a look at overall evolution of graphene over the years, this is where in 2004, the quantum Hall effect, then around 2010, Koridin realized that, okay, if you put graphene inside boron nitride, the mobility jumped immediately, and the fractional quantum Hall effect. But if you take a look at since 2016, a lot of monolayer graphene research is essentially being governed by the looking for hydrodynamic behavior, because now we are in that regime where certain aspects of gauge gravity duality can be explored. Of course, there are twisted bilayer graphene and other topics, but pure monolayer graphene research has very strongly been in this area since 2016, 2017, 8. Okay, so as far as, I don't know, this, oops. Yeah, so there are several areas, several directions where people have been looking for it. For example, this was 2016 where the first violation of the Weidemann-Franz law was reported. Then this is from Berkeley group, is looking at the terahertz spectroscopy, showing that tau inverse, that is the scattering rate, is actually in the order of kBt by h cross. From ICFO group, showing that Weidemann-Franz law is broken. Heat goes much faster than charge. And there are recent work that has been given for magnetoresistance and so forth. I will not go into that. The problem in all these, that's one component is still missing, and that is the universal conductivity that you would associate with a quantum critical system. That has still not been observed in spite of 8 or 9 years of this. As a result, there had been oppositions to this, and if you take a look at this data here, there's a peak in the Lorentz number, and that is not expected. So Shankar has actually published something showing that it is in principle possible to explain the hydrodynamic, explain the Weidemann-Franz law data simply on the Fermi liquid platform, assuming a little bit of stretched, a little bit of gapped graphene. So there are questions. So in order to solve that, we would like to know the universality of the quantum critical graphene. What we have done, we have taken a look at extremely high quality devices for graphene, measured the electrical transport, and use Johnson noise thermometry to measure its thermal conductivity. And instead of using an extension or an extrapolation of conductivity to the Dirac point, we have used the second theorem or the second equation of the relation between kappa, the thermal conductivity, and electrical conductivity to evaluate what the sigma q really is. So that's the experimental strategy that we have used here. I'll go quickly. Here, essentially, for experimentalists here, I don't know how many are here, we have made graphene devices which are relatively high quality. By utilizing a uniqueness of geometry, we use rectangular samples and use certain experimental post-processing, and that led to extremely high mobility. I'll show you in a minute. Then compared to the state of the art, you can see the electrical resistivity of graphene as a function of density is given by the sharp bell-like curve. So if you go to the positive side, this is electrons, this is holes. And the sharpness determines how mobile or what the quality of your devices are. Okay, so if I give you a rough number of the kind of devices that we make, This is electrical conductivity of the same three devices as a function of density. And I can calculate the mean free path of charge using simple formulae. And we can realize that usually the mean free path turns out order of magnitude to be size of the device or even larger. So which means the momentum relaxation in our devices happens primarily at the boundary of the sample. This is not something completely new. There are now several groups which are making devices which are so good that the electrons start scattering only at the boundary rather than inside the device. And this is something which is very good and necessary. Typical, if I convert this to mobility, although mobility itself does not mean much these days, it's extremely high in several of our devices. So typically, if you take a look at the devices that we measure, it's somewhere, I'm going to show you the data from this quality of devices. Okay, so if I have high quality electrical conductor, there are usually three regimes of transport. One is ballistic, in which the electron can go from here to here without suffering any collision at all. Diffusive, of course, that's not important to us because it's everywhere. Scattering at, in a conductivity is proportional to the mobility and density, whereas in viscous regime, where you can show that when the momentum conserving scattering, where the electron and electron scatter more often than the electron and impurity scattering, then you have a situation where the electrical conductivity is proportional to the square of the width here and the square of the density. So these are typical experimental signatures. That what we will look for. So this is a typical example. You can see at very large density, it appears to converge towards the ballistic conductance, that is root of n. Essentially, root of n comes from the fact that conductance is proportional to the Fermi wave vector, and this is something which we can say that's typically quasi-ballistic regime. In this regime, if you can see here in the disorder part, where the electrical conductance is constant with respect to density, that is where the system is incompressible. This region is because of the disorder, but as you increase temperature, this flat region increases, which essentially is because now we are getting into the thermal regime. So thermal regime is given by the fact that there are excitation of charge from valence band to the conduction band, leading to this region. And this is the region that we will be looking for. And this is the thermal region where the temperature becomes the most important energy scale, and disorder is unimportant. You can see the disorder is typically of 5 to 1, 10 to the 10, whereas we can go up to 3 to 4, 10 to the 10, which is significantly high. Okay, so this is the region that we would be mostly converting, looking into. Okay, so first question to answer is that, is it a system clean enough? Is the system clean enough that the impurity scattering is not important, but it's primarily the electron-electron scattering that dominates the electrical transport? The first thing to do is essentially convert the density into the typical distance between the electrons, and we plot the conductivity as a function of this number normalized by the width of the sample. And this is effectively something like a Knudsen number. When you have a fluid goes through a pipe with a diameter W, when the typical distance between the molecules becomes smaller than the width of the system itself, you go into the viscous regime. And you can see the conductance, when I normalize as a function of LEE over the W for several samples, the ballistic to viscous regime can be identified by conversion at this transition happening at roughly of Knudsen number of 1. That's first evidence. The second one, of course, is the width dependence. You see the width of this, and what we do is we look at the conductance of several samples from 1 micrometer width to about 6 or 7 micrometer width, and we see that in this regime, which is Fermi liquid regime, the conductivity is proportional to the square of the width, showing that this is again possibility of a viscous hydrodynamic flow of charge. What the purpose of showing this part is that to establish the fact that electron-electron scattering indeed dominates in our system over the impurity and phonon scatterings. And the viscosity that you get is a kinetic viscosity as a function of density. It's in the order of 1 meter per second. This is typically what has been observed by the other groups in the world as well. And what is interesting is that you can see the viscosity is relatively device independent because they are primarily determined by the distance between electrons rather than the details of the materials per se. One part is done. The second part is the thermal conductivity. Easy. I'll now go to the detail again, measure the Johnson noise thermometry to measure the electron temperature at various densities and temperatures. So why do we need electron temperature? So suppose you have graphene and between two leads, and width of graphene is W and L. I apply an electric field. It's essentially a Joule heating that leads to, you solve the thermal equation, and then you can solve the equation for temperature as a function of distance. It looks like the temperature from the bath temperature, it goes up and comes down, and you can get the average electron temperature in the region given by, which is this simple equation where the electric field is E and this curly L is the Lorentz number. So you can, if I measure the electron temperature as a function of E, I can get the Lorentz number directly from the experiments. And this is exactly what we have done. You can see delta E temperature as a function of electric field. It's kind of increases flat and then starts increasing linearly, and this fit gives us the exact value of Lorentz number. So what happens now, if I plot the Lorentz number as a function of density, and this is one of the most important, first interesting result. If you take a look at, this is 3 samples I'm going to show you. The D1 is the most disordered one, and D2 and D3 are the clean samples with mobilities more than 1 million at low temperatures. The Lorentz number changes from the Dirac point to a density of about 4 or 5, 10 to the power of 11 by nearly 6 orders of magnitude. And it goes from much higher than the Wiedemann-Franz law value to a much lower number, nearly 3 orders of magnitude below that at higher temperature, at higher densities. So this is a giant violation of Wiedemann-Franz law. Wiedemann-Franz law is not even in the picture anymore. If I look at it, the same thing at different temperatures, as you can see, this is at low temperature, this is at high temperature, and the equation that fits full thing is given by the simple Boltzmann expectation, assuming of hydrodynamic transport. So this is, the red line is the fit to this, and this allows us to get the value of L0, which gives us the entropy as well as thermal entropy as well, thermal enthalpy as well. Okay, so if we have got thermal conductivity, Lorentz number, and we have got the electrical conductivity, we have thermal conductivity. We plot thermal conductivity as a function of temperature in these systems, and for different densities, charge neutral point, and then 10 to the 10, 10 to the 11. Typically, you see a non-monotonic behavior, and this is because below 100 Kelvin or so, the system becomes inhomogeneous. We have been, by cleaning the system, by using high mobility electrical systems, we have been able to reduce the inhomogeneity temperature to about 100 Kelvin. So it gives us about 100 to 300 Kelvin of region where we can look for thermal behavior or other properties of ADS-CFT. So this is the region of inhomogeneity. So most of our analysis will be above this, where the temperature is higher than the impurity temperature. In this regime, that is higher than 100 Kelvin or so, if I plot the electrical conductivity and thermal conductivity together, and we find that the electrical conductivity is inversely, thermal conductivity is inversely proportional to the thermal conductivity. So electrical conductivity. So that is one of the key expectations of relativistic hydrodynamics. It's opposite to what you would expect in the case of a diffusive system. Now we are ready to calculate what the universal conductivity is, because if you look at it, the sigma q is given by rearranging this equation: thermal conductivity, which is experimental; electrical conductivity, which is experimental. The LMR, the momentum relaxation length, is primarily, in most cases, the width of the system itself, because momentum relaxation occurs only at the boundaries in most of our devices, multiplied by the value of enthalpy, which is also experimental from the fitting of the Lorentz number with density. So if I do all these, and then we just put it together, this is sigma q as a function of at different temperatures, where we see is at high temperature, above 100 Kelvin, it kind of converges to a number irrespective of what the density is. Actually, at low densities, slowly, they all converge into a particular number in these systems. If I plot this as a function of Fermi temperature divided by the actual temperature, so this is, when Fermi temperature is by T is below 1, this is the thermal regime, we have a complete, quite impressive convergence where this number turns out to be somewhere around 4 plus minus 1 E squared by H. There are 7 different devices and temperatures. Now, that's good. Now, if I ask the difference that with this universal conductivity of graphene and what we measure, we have been measuring for a very long time in sigma minimum. So if we have taken different samples of different disorder, and we can calculate by extrapolating the value of sigma towards n equal to 0, and we can see that this is what completely non-universal numbers are, whereas the sigma q, which is essentially taken from the limiting value at below, well below the Fermi temperature, well above the Fermi temperature, they are much more clustered and within plus minus 1 of 4 E squared by H. In this context, the number 4 E squared by H needs to be calculated and found out, but if I look at this old calculation of superfluid insulator transition, sigma q is expected to be around 4 E squared by H multiplied by the universality class phi sigma, which is in the order of 1. Good. So with this, one of the questions that we want to ask here is that, okay, we have found out a way in which probably the quality of graphene has been sufficiently good that it's a quantum critical system. Probably some properties are universal. But then, are there signatures which are analog, gravity analog, and can we pull out some of the aspects of black hole physics? And one such aspect is the viscosity over entropy ratio. Question is, just to give a very quick understanding of what happens there, typically the viscosity is dimensionally is h bar multiplied by some density. Now, when you are talking about something which is thermal, purely thermal system, then we can say that this n is nothing but the thermal excitation, the density of thermal excitation. And also, if you look at entropy of that system, then it's essentially a kb multiplied by the number of excitations you have. So a far more rigorous derivation is here. This is just to show that probably in some limit, the entropy, the viscosity divided by the entropy would lead to what you call a holographic limit of given by the h bar by kb ratio, which is the minimum viscosity that a quantum fluid can have. That's the goal. So can we measure this in our systems? So this is the minimally dissipative flow. How do we calculate this? In the case of Fermi liquid regime, getting the viscosity from the dependence of conductivity on the width of the sample and other parameters is easy. But we are talking about the thermal regime, which is a non-viscous component. So we would like to define what is an effective viscosity of the system. So a viscosity here is enthalpy density multiplied by the scattering time. And this scattering time in the thermal regime is Planckian scattering, which is h bars by alpha squared kBt, where alpha squared is the interaction constant. If I look at the electrical conductivity as a function of density, you can see that this, at low values of density around but above the inhomogeneity part, is actually going into the quadratic density dependence. So which means that I can get the value of enthalpy here by the derivative of conductivity with respect to n squared. So this is, again, an experimental quantity. I'm not going to assume what the value of enthalpy is. So from the experiments, we take the value by derivative here, and this number comes out to be this. So this is the enthalpy, this is the viscosity. And of course, if I plot this, I got the numbers here. Typically, this is how the enthalpy the viscosity goes with temperature. At high temperature, above the inhomogeneity temperatures, they all move towards asymptotically to the quadratic T-squared dependence, which is something which is expected in the thermal regime. Okay. The entropy, again, is an experimental quantity which we get from the fitting of the thermal conductivity and taking the scale over which the thermal conductivity changes and the value of Lorentz number at the Dirac point. So with these two numbers, then I calculate what is the ratio of eta and STH, and this is what we get. So these are 5 or 6 different samples. Yeah, I'm almost done. There are 5 or 6 different samples. What's interesting here, this is the sample which has got the highest disorder, which is disorder in our case is determined by the minimum value n min, where below which the density cannot be changed. The graphene has become incompressible in nature. So, and this one, the red one, is the cleanest sample. Its mobility has gone up to nearly about 10 million, if that's a number that you would like to trust. And what's interesting here is that the value of the viscosity over the entropy in the units of h bar by 4 k by kb starts approaching the value of universal holographic limit at sufficiently large temperature. Going to higher temperature, apart from the fact that experimentally it's difficult, it's actually becomes phonon dominated, so the value of the mean free path starts decreasing. So we usually avoid going to too high a temperature. But this is something which tells us the importance of reducing disorder if you want to create systems that would be true manifestation of the gauge gravity duality. So if we want to build some things like systems like that. I'm done. This is the conclusion. Then it's a new regime, or it's a I wouldn't say new, but there are a lot of people here who can make extremely high quality graphene samples. So it's a condensed matter system for testing gravity analog models. We are in a situation where our disorder in the system is sufficiently low that some of the quantum critical physics can be approached with a new way. We have a giant thermal conductivity close to a Dirac point, over 300 times larger than that of semi-classical magnitude. We have seen the obviously breakdown of Wiedemann-Franz law. First evaluation of the quantum critical conductivity, which seems to be in the order of 4 e squared by h, independent of devices and the materials. And probably we are now in a situation where graphene, the hydrodynamicity of the graphene in these high quality devices are moving to with minimally viscous flow of charge that is expected in a strong quantum critical systems. Thank you very much for your attention.
Okay, we can take questions.
Philip.
Yeah. Can somebody come there?
Very nice talk.
Thank you.
Going back to one of the data you showed that temperature increase at some bias volt.
Yeah, that's the Johnson noise measurement.
Yes,
okay, yeah.
I thought kind of the temperature the rise is very high.
Yeah.
So in a sense, it is kind of many times higher than the bath temperature.
That is correct, yeah. But that is the phonon temperature that you're talking about. So it's much higher. The electron temperature can go much higher than the phonon temperature. There's no doubt about that. But we are essentially completely decoupled from the phonon system anyway. So we are only talking about the electronic thermal conductivity. So that probably doesn't hurt us.
So when you just say that this is kind of your slope, what is it, the base electronic temperature you just
This one? Oh, yeah, sorry. So, yeah, so this particular one was taken at, okay, so we have subtracted the base temperature. This is, I would say, okay, this is a very high increase. So this will be at the 20 Kelvin or 30 Kelvin temperature. So this is the phonon temperature is about 20 Kelvin or so.
Okay. The other the other part is you mentioned in the beginning that higher temperature phonon will just kind of kill this hydrodynamics. And you briefly mentioned certain temperature that you start to kind of see the phonon effect.
Right.
Can you just elaborate what is the temperature range is?
Yeah, actually, it probably starts even before room temperature. So when we measure the mean free path, we start seeing it starts decreasing even above 200 Kelvin. So 300 Kelvin, already the phonons have started taking place. So I would say above 200 Kelvin, you already start seeing the effects of phonons. Higher you go, it becomes much stronger.
Thank you.
Yeah, really fascinating talk here. Yeah.
Hi.
Really fascinating talk. Thanks. So the eta over S, I wasn't so sure how good it was in the end. Can you explain again? I remember
sorry.
The ratio, the viscosity.
Oh, right, the viscosity ratio.
How close it actually is to the
Yeah, the best of our devices, we could go up to 4 times the holographic limit. So this is and this is entirely experimental, which is one of the things that we would like always to say. So if you see this one, this is 1, this is the holographic limit. And the best device, which is this guy, we could go up to about 3 to 4 of these square waves. There are, I mean, whether it is limited by the electronic interaction in graphene or it's limited by the disorder, I'm not sure.
But why it shoots up then for low temperatures? Is the disorder in the system?
Yeah, that's right. So this is the disorder. So actually, yeah, so this part is extremely disordered. This is an inhomogeneous part, so you don't. And the second thing is the TF, the Fermi temperature divided by temperature, must be as small as possible in order to make the thermal energy as the only relevant energy scale. And that happens only at higher temperature. So if you want to see this convergence or the saturation to the holographic limit, you need to make TF, the Fermi temperature over actual temperature, as small as possible. That's why it's a higher temperature that's of more interest to us.
And just final question, maybe, what are the residual disorder in the system? Is that wrinkles in the graphene, or what?
The residual disorder.
Yes, well, where does it come from?
The residual disorder comes from the substrates. Primarily, when you make these condensed matter systems, you have to put the channel on a substrate. And that substrate has a lot of trapped charges. They apply Coulomb potential on the electrons and then scatter them. So what we have done, or many other groups in the world has done, essentially remove those traps as effectively as possible. So that's where we are. Yeah.
Hi, Shankar.
Yeah. Okay, Shankar. Shankar.
So, Arindam, I saw your paper. I haven't had a chance to study it, but trust me, I will. So the C hydrodynamic effect, or any of the, I call it intrinsic graphene effect. I like that terminology better.
Sure.
What you need is a temperature which is very high, quote unquote. It's somewhat counterintuitive because of puddle.
Absolutely.
So can you tell me what your Fermi temperature corresponding to your puddle density is? What is the number?
Yes.
What is the number?
100 Kelvin. 80 to 100 Kelvin.
80 to 100
80 to 100 Kelvin.
Then
so
I doubt very much you're saying. Let me tell you why.
Yeah.
You need to be at a temperature much, much higher than that to see intrinsic graphene behavior.
Of course.
But your phonons are coming at 200 Kelvin.
Correct.
So you have to be much higher than 100 Kelvin.
Right.
But you have to be much lower than 200 Kelvin.
Right.
I don't see data.
Right.
I mean, there is nothing left. Much higher than 100 and much lower than 200.
Right.
You have to take data exactly at 150 Kelvin.
So you can...
Only at 150 Kelvin, you can see the physics you're claiming you have seen.
Yeah.
Just at 150 Kelvin.
I can tell you how to get around with it.
I do not know what's going on.
No, I'll tell you how we get around with it. So the idea is that you're absolutely right, that you start your inhomogeneity temperature is about 80 Kelvin. Phonon starts kicking in about 200 Kelvin. So it's a very small.
I'm your numbers.
Right. Yeah. So what you do is that you start asking the question that what is the momentum relaxation length? So see, what the phonons will do is that it's going to relax the momentum. It's going to change the momentum, which we don't want if you want to have a hydrodynamic system. Now, even if the phonons are kicking in at 200 or so, by the time it really affects the momentum relaxation length compared to your device sizes, it still has to go some certain distance. So that's what helps you.
No, I understand all that since I've been working in for 20 years, but I don't see a calculation justifying it.
I
just gave you a dimensional
I thought
argument.
you would do this.
No, I just gave you a dimensional argument. You have to be much higher than 100 Kelvin and much lower than 200
Absolutely.
Kelvin.
So actually, I showed Shafiq Adams' work. I mean, they actually identified...
Shafiq results are wrong, so let's not discuss.
Fair. I didn't do this.
Okay, Abhishek, yeah, sure.
Very informative
Yeah.
and very
Thank you.
nice.
Yes.
So I have many questions. I'll ask outside, but one question is, you said that you have obtained 4 times the KSS bound, right, in
Yeah.
the viscosity regime.
Yeah.
So do you know what is the Knudsen number?
Yeah, the Knudsen number is smaller than 1, always. So the way we identify the regime where we calculate this, excuse me, this number at this region of temperature, the Knudsen number is much smaller than 1. So that's the boundary below which we consider the hydrodynamicity. Above that, it's all ballistic.
But precisely, you don't know right now that why you have 4 times.
We can calculate. No, we know what the Knudsen numbers are because we know
means why you got 4 times the KSS
Oh, well,
bound.
I don't know why that limit is coming because 1, the graphene is strongly interacting, and that Knudsen number of 1, the viscosity over S will approach 1 in infinitely interacting system. And graphene is not an infinitely interacting system. Its interaction number is about 1 or 0.5 maybe. Okay, so I don't know whether that's the reason why we haven't approached the holographic limit, or looking at the dependence of this number on disorder, I don't know whether this is because of the finite remnant disorder that we haven't approached the holographic limit. I don't know this answer.
Thank you.
Yeah, Abhishek.
Yeah, so I mean, so since it's flowing like a fluid and you calculated the viscosity, so I
Right.
wonder if you looked at calculated the Reynolds number, and then presumably this is in low Reynolds number, and
Right.
can you actually push it so to get into
We
like,
can, and that's what we would like to do in the next phase of this work. Is what we have done is we have looked at the electric field dependence of Johnson noise, electronic temperature, thermal conductivity at low electric fields. Now we are going to push this to higher electric fields. There are already evidences of nonlinearity in this, but these are difficulties without a proper theory and calculations. It is hard to sort of interpret. This is actually, yeah, I mean, we are looking at nonlinearity in strong electric fields. And that's the way to get the higher Reynolds number.
what's the Reynolds number now?
I don't know. I mean, we have to calculate that. But this is essentially, I don't know, this is laminar flow. I mean, I don't think you have gone into, yeah.
Yeah, spent.
Yeah, spent
Hi. So, do you know a system in which the viscosity to entropy bound is saturated and
To one?
yet,
In a condensed matter system,
yeah, and
No.
No.
there is no, as far as I know, there is no condensed matter system in which a viscosity over entropy bound of 1 has been achieved. There are theoretical predictions of certain hyperspites or something, I'm forgetting that, which are Kagome materials, in which it is possible to get, because the interaction is so strong there are predictions, but there are no experimental evidences.
Okay, so the next part of my question was that suppose if that bound is okay, then can we have a system in which the Wiedemann-Franz law is actually valid? I mean, I do remember something like this.
I do not see the
No.
reason why should the Wiedemann-Franz law be valid in a system which is not diffusive.
Ah,
Because at the end, Wiedemann-Franz law is universally, I mean, the K by sigma is universal because you have the same excitations that carry charge and heat. In this case, that's not the case.
okay, good, thanks.
Okay, any other questions, comments?
Oh,
Well,
and I had
yeah,
asked.
sure.
Yeah, so thanks a lot for this nice talk. But I'm just, maybe this is very naive, but I'm trying to understand where is all this going. So let's say you're able to show this. So then what?
Well, I mean, there are other phenomena which is connected black holes that is accessible to me on my table in graphene system. And
Okay, so there are some things
course.
that, okay,
this
so
is
you
just
have,
this
you're
probably
just not
start.
telling us right now, you know all the things you want
Yeah,
to do.
we
Okay.
can talk about it.
Okay, thanks.
Sure.
Okay, I don't see any more hands. So let's thank the speaker for a very nice talk.
Thank you.
Yeah. And so this closes the session.